Okay, so far we have talked about the kinetics of chemical reactions when we are converting substrates into products. Recall that we looked at our graph where we were looking at reaction coordinates versus free energy levels. And we talked about a spontaneous reaction where the free energy of the substrate is greater than the free energy of the product. If we calculate the free energy change of this reaction, which is delta G 0 prime, we're going to see that this is going to equal a negative delta G, which means that this reaction is exothermic. So this reaction will proceed forward. Now the other type of reaction we looked at, other chemical reaction, is where the free energy of the substrate is less than the free energy of the product. In this case, we are talking about a free energy change, delta G 0 prime, standard free energy change, that is going to be positive. In this case, this is an endothermic reaction. Essentially, it's going to require energy to transform the substrate into the product. This will not be, of course, a spontaneous reaction. Now, when we move into enzyme catalyzed reactions, the situation is a little different because we have to consider the role of the enzyme in the chemical reaction. In the straight chemical reaction, we are just looking at a substrate or reactant that converts into product. With the enzyme catalyzed reaction, we need to consider the enzyme plus the substrate in solution. Now, when these two come together, the substrate is going to bind to the enzyme, and we are going to form an enzyme substrate complex. This complex is called the transition state. It's a transition state on the way from the substrate to becoming a product. But the transition state is very important because this is how the enzymes are going to function in a thermodynamic manner. Once we form the enzyme substrate transition complex, then we can now form the product. The enzyme typically performs a chemical modification of the substrate to yield product. Now, if we place this reaction on a graph, as we've seen before, reaction coordinate, free energy change, free energy state, what we can measure is that if this is the free energy of the substrate, typical enzymatic reactions requiring enzymes will look like this. Now, several features to keep in mind here. This is the chemical reaction in the biochemical sequence. We have substrate being converted into product. So this difference in free energy equals a negative value. So technically this means this is an exothermic reaction. This reaction can be considered moving forward and spontaneous. Now, spontaneous is relative because we have another level of energy here that is required for this reaction, and this is called the delta G activation. What this simply is the amount of energy that needs to be placed into the reaction in order to get through the transition state of the reaction itself. So this of the chemical reaction is the transition state. It takes a large amount of energy to take the substrate to a transition state. Once we reach this level, then the rest of the reaction is a negative free energy change and will move forward. But we have to put this much energy in. Now, does this reaction occur without an enzyme? Sure. We can, over the course of time, some environmental change might occur that we can put this much energy into a reaction to get it over this activation barrier. Now, the problem with this is that this could chemically take many, many years. Let's say, for example, 10 to the 6 years to overcome this activation barrier. That means the reaction will go. Chemically, it will move forward because of the negative delta G on the transition, the free energy change between substrate and product. Of course, we do not have 10 to the 6 years in order to wait for this, so this is where enzymes come in and make this reaction essentially go faster. They are going to catalyze this reaction. And in doing so, what enzymes will do is they essentially reduce the activation energy needed to make the reaction go forward. So this now becomes the new delta G activation when an enzyme is added. So now the amount of energy that is required in order for this reaction to move forward is considered the delta G cat for the change in free energy required for the reaction in a catalytic state with the enzyme present. Now this is going to move much faster because in order to get over this thermodynamic barrier, this activation barrier, it's much smaller, so it takes a much smaller input of endothermic energy. So for example, heat inside our bodies are warmer than the environment, so that extra heat can be used into this reaction. The addition of bonding of the substrate to the enzyme, that is going to give off sufficient energy that it will help reduce this delta G activation. Now this little trough in here is the transition state of an enzyme catalyzed reaction. And so we can place the ES complex, enzyme substrate complex, in this trough. And that will represent the free energy change between the substrate and enzyme substrate complex. Now this reaction is going to move much faster because we've eliminated essentially the activation barrier. Okay, so let's look at the mechanism of action of enzymes a little bit closer. So we just saw that enzyme plus substrate will form an enzyme substrate complex. This, of course, we've deemed as the transition state complex. The next step in the reaction is naturally the chemical conversion of the substrate into a product by the enzyme. So we can deem this as the enzyme product complex because the product is still essentially bound to the enzyme. The final step of the reaction is the dissociation of the product from the enzyme. And then the enzyme, of course, is being catalytic. It is not consumed in the reaction, is free to re-enter the cycle and bind substrate to catalyze the next round of reactions. Now, how does this play out? How does this mean on our free energy graph? Let's look at the mechanism. based on what we've seen before. So an enzyme is going to take a substrate at a specific free energy calculation. It is going to reduce the activation energy in order to generate the product. Now we saw that the difference between the substrate and the product is a negative delta G. So that means that this reaction is exothermic and it's moving forward. What the enzyme, of course, is doing, to reiterate, is if this is the original activation energy, delta G activation, the enzyme is essentially reducing this to a much smaller level, allowing the reaction to move forward. Now mechanistically, how do we connect this reaction sequence with the free energy change measured in the enzyme catalyzed reaction? Well, we start out with substrate. At this point, we add enzyme. The enzyme has to bind to the substrate to form our transition complex, enzyme-substrate complex. Well, in order to do this, we have to dissociate water from the substrate in order for it to enter the binding pocket of the enzyme. That is going to take energy. And this needs an input, a positive delta G input of energy, to remove water and salts from the substrate in order for it to enter the enzyme. Now once the substrate enters the enzyme pocket, then it reforms bonds with the enzyme. And here we have a negative delta G. And these are bonds formed between the substrate and enzyme. That, of course, is exothermic. Now the next step is the step that is the rate-limiting step, and that's the conversion of substrate to product. This is usually a chemical event, such as breaking a covalent bond in the substrate to release products, and that is going to take energy. So this will be a positive delta G, and this is the substrate to product conversion. That's an input of energy. That input of energy could come from, say, energy derived from torsion inside the enzyme. And release of that torsion could provide the energy necessary in order to convert the substrate to product. Once that happens, the product can now reform bonds with the enzyme. Reform bonds in a different way than the substrate originally did. That would be a negative delta G. And that negative delta G is the bond energy that is released when the product binds differently to the enzyme's active site. The final step here is the dissociation of enzyme and product. This requires a positive input of delta G, a positive input of energy, in order to break the bonds between the product and the enzyme. Then finally, we have a negative free energy change, and this is due to solvation of the product. Once the product leaves the active site of the enzyme, it now reforms bonds with water, hydrogen bonds, and salt bonds, ionic bonds, in order to become fully solubilized in the solvent.